Bismillahirrahmanirrahim. Welcome back. So, for the initial part of today's lecture, there are no slides. So, if you want to record what's happening, you just need to take notes. So, the good old-fashioned way. और उसके बाद जैसे ही हम slides पे switch होंगे, उसके बाद से there will be slides. So, until then, there are no slides. All right, जी. Okay, so we're going to take maybe 3 steps back before jumping across the moat. So what I'm going to do in front of you, hopefully in the first few minutes of the class, is that we're going to build a bunch of neural networks. We will initially use them for what we traditionally used to use them for. Then we'll vectorize them. Then we'll see how we can change our perspective a little bit and start using those neural networks for something more interesting. देन एज हमारी मशीन लर्निंग के अंदर आदत है जब भी हम कुछ बना लेते हैं फिर उसकी बुराइयां करते हैं फिर हम इस मशीन लर्निंग के मॉडल की इस न्यूरल नेटवर्क की बुराइयां करेंगे एंड फ्रॉम देयर होपफुली वी विल टुगेदर come up with a new design that's going to take us maybe 3 lectures from now till some new interesting models. Okay, so let me create a fake problem for this neural network जो मैं बनाने लगा हूँ. इनफैक्ट मैं खाली एक न्यूरॉन बनाने लगा हूँ. And the problem for those of you who are from my own machine learning class, they have already seen that a million times. So remember the same problem where we used to predict whether someone has heart disease or not based on a bunch of features like their blood pressure, systolic and diastolic, maybe their weight in kilograms or grams or whatever, their height in inches. So let's say we have these 4 features. And based on these 4 features, we want to predict whether that a particular person has heart disease or not. We're doing good old-fashioned supervised machine learning, and we want to create a neuron for this. Okay. By the way, ये अब तक का जो मैंने बात की है, you should all be experts of this. तो आपको ये सब कुछ बहुत जाना पहचाना लग रहा होना चाहिए. So let's assume these are my x0, x1, x2, and x3, my 4 features. This neuron itself has 2 parts. The first part, where it linearly combines these features by after multiplying each one of them with a weight. So it has a bunch of knobs here, W0, W1, W2, and W3. By the way, fair warning, बहुत तवज्जो से सुनिएगा किसी एक सेकंड के लिए भी इस फ्रेम ऑफ माइंड में ना जाइए कि मुझे ये आता है. It's going to switch from आता है to नहीं आता very quickly. So I want you to be paying attention to everything and keep feeling happy and warm while everything is just a revision. Okay, so this is the place where they combine together. So we usually write this as W naught X naught plus W1 X1 plus and so on and so forth. I don't want to vectorize it just yet. So I can just do it like this. And I can do Xi and Wi. I have explicitly not written a bias term here. I could have written a bias here, B. We know how to deal with biases. We also know how to absorb biases. So we don't care for them. So let's assume कि हमने यहाँ पे एक नया x introduce कर दिया जिसको हमने जिसकी value 1 कर दी and that उसके साथ जो चीज multiply हो रही है वो bias है. So I just don't want to overcomplicate anything which we can simplify. So ये वो जगह है जहाँ पे we have a linear combination. What's the next step for this neuron? We pass it through a nonlinear activation function. So suppose your sigmoid. So this is the place where you do A is equal to sigma Z. So you get your A from here. ये A हमारी hypothesis है. We also call it the y hat. Okay. This thing was the forward pass. This was the inference of the neural network. Given these weights and given these values of the features, इसने हमें एक output दी है. That output is a number. What are the ranges on that number? What are the ranges on this number? Quick, bol pade. 0 to 1, because we have passed it through a sigmoid. If this would have been a tan H, the range would have been -1 to 1. If this would have been a ReLU, the range would have been 0n. Yeah, 0 to infinity. कहीं तक भी जा सकती थी. If this would have been a Ricci ReLU, the range would have been a very small negative number to infinity. Okay, and then there are many others. We'll talk about SWIGLU, we'll talk about others. Right now, we're not talking about them. Right now, we just want to see that, okay, this y hat looks like a probability. ओके I'm just thinking कि मैं कहाँ पर वो वाली बात करूँ अभी करूँ या ना करूँ okay I don't have to do it right now okay so all right so the forward pass is done at this point if we were just testing this neural network running this neural network our task is done हम अपना काम कर चुके हैं if we would have been training this neural network then दिस मीन्स कि ये जो मैंने इनपुट दी थी ये मेरे ट्रेनिंग डेटा सेट में से कोई एक इनपुट थी जिसकी मेरे पास एक्चुअल आउटपुट मालूम थी सो द रियल वाई इज नोन द हार्ट डिजीज स्टेटस सो सपोज हैविंग हार्ट डिजीज मीन्स 1 एंड नॉट हैविंग हार्ट डिजीज इज 0 ओके सो यहाँ पे हमारे पास एक एक्चुअल 1 और 0 मौजूद है दिस इज लाइक योर hard max if I were to call it and this is a probability like value between 0 and 1 which is saying कि इसको heart disease है या नहीं okay what's the next step what do we do here we calculate a loss function so we have a loss function we calculate the loss y hat y the loss tells us how far away were we in our prediction that's why this needs to be smooth and this we don't care about whether it's smooth or not a loss function should be capable enough to figure out the distance between the two based on that distance if the distance is massive we would ideally want to go back and tell these weights, hey, you didn't do a really good job. So move in some direction. And if they were close, we'll be just gently nudging. We'll be going back and saying, yeah, you're almost there, just a little bit more. So तुम थोड़े से बड़े हो जाओ, तुम थोड़े से छोटे हो जाओ, तुम फलां हो जाओ, and so on and so forth. So these are the knobs that you are turning in response to how far away you were from the output. What we usually use at this point is our cross entropy loss. So the way your cross entropy loss works is that it is essentially just a comparison. We have done many intuitions of this before, so I won't do that again. But what I do want to do at this point is to figure out how we take this loss and how we go back and let's say assign some value to be changed to this, for example, this weight W0. Okay, remember what we used to do? We used to say पूरी आउटपुट में इतनी गलती हुई है अब मैंने देखना है किसका कितना कसूर है W0 तुम्हारा कितना कसूर है W1 तुम्हारा कितना कसूर है W2 तुम्हारा कितना कसूर है how do we do that we take the partial derivative of the loss with respect to whatever we want to find out कि उसका कितना कसूर है we do it usually using a chain rule so we go back from here one step at a time when we're doing logistic regression we don't care we usually directly calculate delta L delta W0 for example but when we want to do it for a whole neural network we can write this in a more detailed manner who can help me writing this so delta L y hat with respect to y hat which was a right so with respect to a and then into delta a over delta z and then into d over the partial derivative of z with respect to W0 रिमेंबर इससे ये इंश्योर हो जाएगा कि हर स्टेज पे ये डेरिवेटिव कैलकुलेट हो सकता है वी आर जस्ट कैलकुलेटिंग इट at one step at a time right and then we can keep going back if this would have been a bigger neural network this is all revision by the way revision from the middle of the last semester जो मैंने आपको घर से करके आने को कहा था आज okay so once you do that this gives you the proportional contribution of W0 in this loss so now in this plane, ये cost function है. We want to nudge this W naught in the direction where the loss would reduce. So remember the old diagram जिसमें हमने simple करके इसको खाली एक convex loss लिया हुआ था. So this is your W naught and this is the value of the loss. And we said okay for example अगर initially W naught क्योंकि randomly initialized था तो उसकी base के ऊपर loss ये आया था we find the derivative at this point the derivative is positive so we define our gradient descent in a way that this positive derivative is subtracted from the value of W so that W eventually gets reduced. W needs to come here. So we want to reduce W somehow. Everyone is with me? सब साथ है, कोई नई बात तो नहीं मैं कर रहा? Okay. So we define the update function would simply be your W naught T plus 1 is equal to W naught T minus alpha times derivative of the loss function with respect to W naught. Right? This is what we know. ये हम सब इससे पहले सीख कर आए हैं. This was your gradient descent for logistic regression. Okay. Suppose now अब यहाँ पे कुछ चीजें अपने जहन में वापस ले आते हैं. और ये जो मैं बात अब रिवाइज करवा रहा हूँ ये सिर्फ आज के लेक्चर के लिए नहीं है. This will apply to many lectures in the future. Okay. What can you tell me about the distribution of values in this A? If I were to assume that Z was a uniform distribution over the entire range of Z, what was the range of Z? Z कहाँ से कहाँ तक हो सकता था? Minus infinity to positive infinity. So let's take the hypothetical assumption. It's a flat distribution. If this is a flat distribution, what do you expect here? What would the A values look like in terms of a distribution? So A की range क्या है? 0 to 1, right? So if my Z was a flat distribution, then my A would look like what? We should know this. We never said it like this before, but it's just like one step from what you already know. In fact, इस पे machine learning के कोर्स में काफी सारी बहसें हुई इसी बात के ऊपर थी. इसका जो जवाब है वो बड़ा तकलीफ देह है. It hurts the heart. Mathematicians write sad poems about this. In whatever way a mathematician can write a poem, they do. सिर्फ 2 से 3 हाथ खड़े हो रहे हैं, which is sad. I should write a sad poem about you with the help of my chat GPT. But yeah, okay. Enough. Shabash. Shabash. Great. So it's gonna be somewhat like this. It's gonna be a bimodal distribution. दोनों साइडों के ऊपर ज्यादा वैल्यूज होंगी, सेंटर की तरफ कम वैल्यूज होंगी. Because it's a property of your sigmoid. Remember your sigmoid? So it's like this. And if you remember, इसका जो शराफत का जोन था, that was almost between -5 and 5 या -4 and 4. So this is my Z and this is my sigma Z. Then it used to behave well in this zone, but beneath this zone it was close to 0, and after this zone, before this zone close to 0, after this zone close to 1. ये बड़ी जल्दी 1 या 0 पे चला जाता था. ये वाली प्रॉपर्टी भूलनी नहीं. We जब we initially found out about this, the relationship between us and the sigmoid got a little bit tense. We fought a lot. There was a lot of name calling, blaming. But then we found some really interesting places where the sigmoid still remained an amazing function for us. One of those is when you're trying to convert things into probability like things, 0 and 1. It's still used there. We basically pushed it out of most of our neural networks. निकलो बाहर, तुम्हारी वजह से बड़े मसले हो रहे हैं. But we allowed it to remain in the final layers. It still resides there. Secondly, there is also another use case of this. When something has a tendency to be very close to 1 or very close to 0, for those of you especially who are from engineering background, and I can recognize a few, you can think of this thing as a switch. It is a 0-1 switch. It can be used to select things. More specifically, it can be used as an input to a gate. So it can open or close gates for us. ये गुफ्तगू आगे जाकर आनी है, बस आज रिवाइज करवा दी, उस दिन मैं दोबारा ये रिवाइज नहीं करवाऊंगा कि ये गेट क्यों बन रहा है, ठीक है? ओके, सो नाउ वी रिमेंबर द sigmoid, we know how that works. So now we are ready. Basically, we can go in two directions. So which one should I take first? Okay, let me take this one first. This was just for a single neuron. If I extend this concept for an entire neural network, so suppose I have a neural network. मेरे में इतनी हिम्मत नहीं है कि मैं इतनी neurons को जोड़ूंगा. So suppose I have a neural network like this, and I have a few inputs. And let me take a deep breath and connect all of them. Fully connected. So I have a fully connected neural network. Okay. I'm about to ask a question जिसको हम वैसे sanity check कहा करते हैं कि हमारा मॉडल बिल्कुल ही ऑफ तो नहीं है कहीं. इस न्यूरल नेटवर्क की कितनी लेयर्स हैं? अभी भी कोई इख्तिलाफ राय की गुंजाइश है? तुम लोगों को एमएल में किसने पास किया? लाइक आई एम टू ब्लेम, आई नो, फॉर मोस्ट ऑफ यू. But yeah, okay, it's a three-layered neural network. We don't count this thing as a layer because layer होने के लिए आपके पास कुछ बुनियादी असासे होने चाहिए. In this case, the asase is the weights. Things that have weights are counted as layers. Things that don't have weights are not layers. The weights on these edges are the property of these neurons. The weights on these edges are the properties of these neurons, and the weights on these edges are the properties of these neurons. ठीक है, तो लिहाजा इनकी बेचारों की कोई प्रॉपर्टी नहीं है, ये इनपुट है, ये लेयर नहीं है. How many hidden layers does it have? Two. There are two hidden layers. Why do we call them hidden? Raise hand, सिर्फ हाथ, मुझे पता लग जाए कितने लोगों को याद है. ओके, मैं पूछता नहीं, अभी याद आ जाएगा. Okay, so how do you do a forward pass here? You take these four. Now stay with me. This time we're going to calculate. So we have four inputs. It's a fully connected neural network. There are three neurons here. Each neuron will have how many weights? Four. Four weights, one weight for each input. So four weights here, and four weights here, and four weights here. The layer has a total of 12 weights. Okay, good. So we reach this point. At this point, we pass these on here. How many weights would this neuron have? Three. Three weights. One for each output. Just the पहुंच रही है. Okay, and three weights here. So six weights for the layer. And here we have two weights. Okay. After these two weights, you get your y hat. You say, how wrong was I? We say, I have the right answer. We say, let's calculate your loss. We have the loss. Based on this loss, we go back. We come back to this level. We say, hey, wait. How much wrong were you? So यहाँ तक आते आते तो हमें कोई मसला नहीं. It's same. It's this. Because we knew the answer. This was a layer for which we knew the right answer. The problem begins from here backwards. If I want to find out कि इस weight की कितनी गलती थी अपने नुकसान में, अपनी वजह से होने वाले नुकसानात के अंदर, so then I do not have a right answer here. Therefore, I cannot directly evaluate this neuron. Therefore, I call its output to be hidden. And hence the layer is hidden. So all hidden layers do not have any Ys, any gold labels. The layers missing gold labels are hidden layers. Okay, all right, you knew that. Some of you may even remember the example जब हमने ये सब कुछ पढ़ रहे थे तो की थी जिसमें WhatsApp पे एक मैसेज फॉरवर्ड करने से आपने एक बंदा मार दिया था. Remember? You killed the person. So and then we actually calculated your contribution in that person's death. So we actually know proportional blame जितना आपके ऊपर आता है जितना आपको बदलने की जरूरत है. Okay, so now we can go from here backwards and we can keep propagating these gradients backwards all the way till this point. यहाँ तक कि हम इन सारी matrices को ट्रेन करें. Okay, इन सारे weights को ट्रेन करना, अभी कोई matrix नहीं. Okay, इस पूरे मसले में sigmoid पहली दफा विलेन के तौर पे आया था, and the problem was because it's giving you very small values. Therefore, after so many multiplications of the chain rule, you get very small numbers. यहाँ तक कि जब यहाँ पहुंचते हैं और ये पूछता है मेरी कितनी गलती है, तो आप उसे कहते हैं जीरो. मैं कितना बदलूं? कुछ नहीं. I am perfect. So these initial layers start believing that they are perfect. That's the actual problem of vanishing gradients. वहां तक पहुंचते पहुंचते कोई कसूर बचा ही नहीं जो आप किसी को देंगे, वो जीरो हो चुका है या वो अंडरफ्लो कर चुका है. तो फिर आपने कहा था कि अच्छा अपना सिग्मॉइड लेकर इस पे किसी किस्म की क्लिपिंग कर लेते हैं, कोई स्केलिंग कर लेते हैं, या निकलो सिग्मॉइड तुम यहाँ से, तुम्हारी जगह किसी बेहतर को लगा लेते हैं. So we use a ReLU or something like that, and that's fine, and that allows us to continue giving back the gradients to the transferring the gradients to the early layers. Okay, all right. ये सब तो आपको आता है. How many of you remember exactly कि अगर मैं इन 3 लेयर्स के लिए यहां पर लिखना चाहूं, इस लेयर 1 के W नॉट तक अगर मैं ग्रेडियंट पूरा लिखना चाहूं, आप में से कितने लोग लिख सकते हैं बिफोर? ओके, लिखें. फॉर द लेयर जस्ट यूज सुपरस्क्रिप्ट के अंदर लेयर नंबर यूज कर लें जैसे हम पहले करते थे. So for the particular things on that layer, just use the superscript L. For the entire network यहाँ से लेकर यहाँ तक लाना है ग्रेडियंट. वो जो इतना बड़ा सा आता है ना ग्रेडियंट, को पूरा लिखना. Some of you may actually remember these diagrams. If you want to see what exactly you want to call each of the things, you can just use the notation from here. So if you remember, the forward pass used to look like this. So the forward pass is simply you start with your x, and this is vectorized, but yeah, don't worry about that for a moment. Abhi vectorize karte hain har cheez ko. So you start from here, you keep calculating. So using the w and b's, in which case it's just the w. Using the w's, you calculate the z's. Using the z, you calculate the a. This is the layer a outputs जो यहाँ से निकल रही हैं, and then you go to the layer B and the second layer, so layer 2 और layer 2 की outputs of layer 3 और layer 3 के बाद आपका final answer. Okay, if you look at the back propagation of the gradients, you remember this friendly diagram that we used to have, where we say this is the cost, this is the loss that we have calculated. So we say what's the contribution in this cost, what's the contribution of A3, A3 में Z3, और Z3 के अंदर से we calculate the contributions of W's and B's अगर B हो. और फिर यहीं से शुरू करते हुए we go back to A2, from A to Z2, from Z2 Z के weights और Z के biases, और उसके बाद फिर A1 and Z1, और फिर Z1 के अंदर Z1 के weights and biases. Remember? ठीक है. They used to look like this. So this is, by the way, what I asked you to write. Hopefully you wrote it correctly. It's very simple. You know, C के अंदर A3 का contribution, A3 के अंदर Z3 का contribution, Z3 के अंदर A2 का contribution, A2 में Z2, Z2 में A1, A1 में Z1, Z1 में W1, और W1 के अंदर जो particular W में आप interested हैं, that particular W. So let's say W उस layer का W naught या उस layer का W1 या W2 and W3. All right. Okay. This was all still revision. Nothing new. Let's take this. Let's vectorize this. Because हमने आज जहां से काम शुरू करना है ना, we'll be dealing solely with vectors now. So इस सब कुछ को हमें छोड़ना पड़ेगा और हमें हर चीज vectorize करनी पड़ेगी. Okay. So let me just write it here. If I want to vectorize this can be represented, the x can be represented by a vector x. The dimensions of x are, बोलते जाएं, dimensions बोलते जाएं. For this neuron जो हमने बनाई हुई थी, it is 4 cross 1. Okay, so this neuron needs to have as its asset a vector or a matrix, in this case a vector, with dimensions what? जो vector इसके पास होगा उसकी क्या dimensions है? Yeah, so 4 cross 1. So your W vector is also 4 cross 1, जिसके अंदर, just to be very clear, अगर यहाँ x0, x1, x2 और x3 पड़े हुए हैं, तो यहाँ पर W0, W1, W2 और W3 पड़े हुए हैं. So when you actually perform the forward inference, you simply do Z is equal to W transpose X. So your W transpose X just brings them in a form जिससे ये multiply हो सकते हैं. So this becomes 1 into 4 into 4 into 1, which gives you 1 into 1, which is just a scalar. So you get a scalar Z, you pass it through the sigmoid, you're done. Okay, chalo. Let's vectorize one of these days. All right, so let's vectorize this using the same notation, but अब मैं चाहूंगा कि अब की बार आप vectorize करें जरा इसको. What would be the size of X? X is the same. It is still 4 cross 1, but this time layer 1 would be different. So अब सबसे पहला काम तो ये notice करो, and let me help you think through. Layer 1 की neuron 1 के पास कितने weights हैं? Layer 1 की neuron 1 के पास कितने weights हैं? 4. इसके पास कितने weights हैं? 4. इसके पास कितने weights हैं? 4. The entire layer, if it is to be represented using a single matrix as it is, then what would be the dimensionality of that matrix? So it will have 3 things, each size 4. So if you want to just write it like this, you can say 4 cross 3, or you could have written it the other way around as well. Totally up to you. Transpose करना है या नहीं करना, आपकी मर्जी है. Who cares? So we used to care in the previous course, we no longer care. Okay. So ये हमारे पास तीनों neurons. अगर मैं neurons के अंदाज से लिखना चाहूँ जिस तरह ये बनी हुई हैं, तो maybe a more intuitive way of writing this would be the other way around. So then it would be just 3 of these, each having 4 things in them. So this vector belongs here, this vector belongs here, and this vector belongs here. Okay. So this is 3 cross 4. So we can do a direct WX here. We don't need to do a transpose for this one. When we do a WX, we get 3 cross 4 into 4 cross 1, 3 cross 1. So 3 numbers, 3 scalars. That's exactly, it matches our mental model. We want 3 scalars here. Then we sigmoid them. So वो तीनों की तीनों scalars जो हैं वो sigma से गुजरने के बाद probabilities में convert होते हैं, and then they keep moving on like this. Tell me the dimensions of this. दो चीजें होंगी, हर एक के अंदर कितने होंगे? 3. So this is 2 cross 3, and this one would be what? एक चीज होगी और उसमें दो होंगे. So this is 1 cross 2. Still with me? कोई मसले मसाइल तो नहीं? Okay, all right. So this is the vectorization of this entire neural network. I can actually keep doing this. 3 cross 4 into 4 cross 1, 3 cross 1, 3 cross 1 के साथ ये 2 cross 3 into 3 cross 1, 2 cross 1, and then 1 cross 2 into 2 cross 1, 1 cross 1, done. This is all you need to do when you want to verify कि आपने पूरी चीज ठीक बनाई है या नहीं बनाई. All you need to do is just match the dimensions and you're done. Okay, all right. We have done the forward pass, we have done the backward pass, we know how the gradients travel, we know how things get stored. One last thing, one small last thing, इस x के अंदर एक value रखी हुई है. If I want to do a gradient descent, okay, let's talk about two things. अगर मैं इसी तरह का forward pass करूं, अब तवज्जो से सुनना है क्योंकि ये बात हमने इस तरह इससे पहले कभी नहीं की, ML में नहीं की. अगर मैं ये forward pass करूं, ग्रेडियंट्स निकालूं और पूरी मैट्रिक्स को अपडेट कर दूं, ये कौन सा फ्लेवर ऑफ ग्रेडियंट डिसेंट है? रेज हैंड्स, डोंट स्पीक. आई डू अ फॉरवर्ड पास हियर, वन फॉरवर्ड पास, find the gradients, populate the gradients throughout the matrix, go back, done, then do another one. What flavor of gradient descent is this? There is a right answer. Stochastic gradient descent. Why? Because we use just one instance from the data set to update the entire matrix. So it's like the crazy rabbit gradient descent, like which jumps here and there and there and there and there. So like that gradient, the one that we love, right? Okay. If I were to do a batch gradient descent using just one forward pass and one backward pass in vectorized notation, we know how to do that. What do I need to change? A0 का साइज चेंज हो जाएगा. So ये है 4 into 1. अगर मेरे पास डेटा सेट का साइज m है तो it's gonna become 4 into m and everything else takes care of itself. So 4 into m, so 3 into 4 into 4 into m, 3 into m. m आपके पास इसने आंसर्स दे दिए हैं आपको. उसके बाद इसी चीज को आगे तक चलाते जाएंगे तो in the end you're gonna get m y hats. m आंसर्स आएंगे. उन m आंसर्स को आप यहां से वेरीफाई करेंगे using m gold labels, and then you're gonna propagate the error back, and it's gonna update the entire matrix. That's gonna be your batch gradient descent. I want to give you 5 minutes to do nothing, just absorb it all. Sometimes I know it could be speedy, just absorb it. So for 5 minutes, बोलने का टाइम नहीं मैं दे रहा, मशवरे करने का नहीं दे रहा, हालात पूछने का नहीं दे रहा, सोशल मीडिया का नहीं दे रहा. I'm trying to make this a habit. Okay, at times I take these checkpoints. So let that be the checkpoint. You have 5 minutes. I won't say anything. And not even questions, nothing. Just think. Hmm. Hmm. So this is a different notation of writing it. My recommendation would be just follow one. Either follow that or follow this. Mix na karna dono ko. So we can rewrite the whole gradient descent in multiple different ways. That's one way. This is another. In fact, the notation varies from every two implementations of it. It's like an algorithm which could be written in many different ways. क्या मतलब कैसे कर सकते हैं? हाँ दो नोड्स हैं लेकिन असल में दो नोड्स नहीं है ना. असल में दो नोड्स के अंदर से पिछली लेयर में कितने थे न्यूरॉन्स कितने थे पिछले में. यहाँ टोटल कितने नीचे एच टू के बाद एच थ्री भी. हाँ दो ही हैं खाली. तो दिस इज लाइक 2 into 2 मैट्रिक्स. ठीक है तो ये 2 into 2 मैट्रिक्स वापस जा रही है. ये वेक्टर है. All right, Ji. I hope you were able to reach some conclusions. I hope you have made peace जो कि अब तक हमने पढ़ा है. Now, let's get down to business. Now we want to make a neural network that takes in a word and predicts the next word. So we're going to build this neural network. We're going to figure out its dimensions and we're going to learn its gradient descent. So step one, you, based on your knowledge of tokenization and uski zarurat nahi hai, embeddings, try creating a neural network that takes in a word from a vocabulary V and predicts the next word जो उसके बाद आना. ठीक है. इस न्यूरल नेटवर्क को बना के इसकी dimensions लिखने सिर्फ. Just do that. One word. एक word लेकर बताता है इससे अगला word कौन सा. From the entire vocabulary. Yes. Yeah. Take in a word, output a word. Just that. For some of you who are thinking along more sophisticated planes, you may have to take some assumptions. That's fine. जो ये वाला प्लस हाँ जो वाला वो डॉट प्रोडक्ट से हो रहा है बिल्कुल. दो चीजें मल्टीप्लाई होती हैं और सम होती जाती हैं. एग्जैक्टली. Okay, who can tell me now? All eyes here. Who can tell me how many? अभी मैं vectorize नहीं कर रहा हूँ. How many neurons do I have or do I need in the input layer? Raise hands. How many? So I'm calling them neurons. Input layer में neurons नहीं होती, inputs होती हैं. Call it whatever. So how many inputs do we have in this neural network? There is a right answer. You can give me a right answer. V. So there are V neurons. I'm not making a vectorize yet. There are V neurons. So let me call this 1 to V. This is one. I'm calling it again a neuron. असल में ये input है, ये एक number है जो हम इसे provide कर रहे हैं. This thing is one. when this word is there. This thing is one when this word is there. So A कहना चाह रहा था मैं तो ये one होगा बाकी सब zero होंगे. That's an unspecified constraint here. Everything else is zero. It is your one hot vector if this would have been a vector. लेकिन मैं अभी इसके neurons बनाना चाह रहा हूँ. So सब जगह zero except for एक one है इस पूरे के पूरे में. That one is saying कि मैं वो word हूँ जो input में जा रहा है. Okay. From here we go to maybe let's make it with one hidden layer. There is just one hidden layer. So I create a hidden layer and let's suppose it has L neurons. Let me make this fully connected. डायग्राम में कितना fully connected लगेगा इसको मैं कहूंगा हस्बे इस्तात जितनी मेरे में हिम्मत हुई लाइनें बनाने की. So let me do that. I don't know why, but it takes a lot of concentration. If I do it slightly with a distracted mind, I miss neurons. Okay, so your two fully connected layers, and then I'll have an output layer. Okay, पहले output का मसला solve कर लेते हैं. Output layer में कितनी neurons होंगी? V. लफ्ज लेना है, लफ्ज देना है, लफ्ज देना है तो V पर मैप करके देना है. So we have V neurons here. And let me make this fully connected. Walter Levin would have been proud of me. Okay, so now you have a fully connected neural network with two layers, one input layer, one hidden layer, one output layer. This layer has L neurons, this layer has V neurons, this layer has V inputs. What I want you to do now is to tell me how many weights would this layer hold? V. V weights. Suppose V was 10,000. We have 10,000 weights here. अच्छा ये बहुत जल्दी ना हमारे नाजुक नाजुक दिलों के ऊपर बहुत गरा गुजरने लगेगा. बहुत सख्त होगा ये हमारे लिए. थोड़ी देर में हम कहने लगेंगे this could not be tolerated. You're telling me there are 300 neurons here and every neuron has 10,000 weights and at each and every time 9,999 of those are zeros? Such levels of lavishness? Yes. Yeah, that's exactly what you're doing here. So 10,000 here, we here, we here, we here, and we here. Okay. Tell me the dimensions. अच्छा चले अभी ठहर अभी wait, no, no, not yet. Okay. How many weights would this neuron have? L. If this would have been 300, 300 यहाँ, 300 यहाँ, 300 यहाँ, 300 यहाँ, 300 सब में. सब लोग साथ हो मेरे? Okay. Now let's vectorize this. If this is a one hot vector, the dimensions of this vector are 10,000 rows, so V rows into what? I'm saying 10,000 again and again just to give you a magnitude of V. This is not the real magnitude of V. Real magnitude of V would have been like a few million, uh, depending on the number of words you have or the number of tokens you have. So वो जो आपने tokenization की थी किसी बेचारे के न्यूरल नेटवर्क के अंदर वो एक एक टोकन यहाँ आके एक अलग न्यूरॉन बन रहा है. Realize that when you're tokenizing. Your actions have consequences. Okay, so V into 1, give me the dimensions of this using a standard notation. L क्रॉस L रोज हैं और हर एक के अंदर V. मैं ये इसका ना ये साइन हटा ही देता हूँ बार बार वरना बनाना पड़ेगा. So either I should call it V a set या V a number. For me now V is a number. Okay. Okay, L cross V. So 300 into 10,000, suppose, if we were assuming L to be 300. Okay. Give me the one for this. V cross न्यूरल नेटवर्क बन गया पूरा. Okay, so let's try this out. If we want to do a forward pass, this is going to be L into V into V into 1. So L into 1, right? उतने ही यहाँ पे आउटपुट्स आएंगे जितने न्यूरॉन्स हैं, बिल्कुल सही है. So L into 1 यहाँ से लिखना, V into L into L into 1, V into 1, which gives us another one hot vector-ish thing. It's not a one hot vector, it's something else, but let's see what this is. Okay, what do we have here? Now we are in uncharted waters, unknown territories. What do we have here? What's the range of the thing that I get here, sir? 0 to 1, a number between 0 and 1. If this is an actual neuron, and it is an actual neuron, it has some kind of an activation. Let's assume a sigmoid. So that means यहाँ पे एक number है 0 to 1. यहाँ पे भी एक number है 0 to 1. यहाँ पे भी एक number है 0 to 1. और इन सब में एक number है 0 to 1. Okay. Are they related? कोई आपस में चाचे मामे ताए हैं या नहीं? Is this output related to this output? Can I say that these together sum up to 1? No. No, we never established that relationship. This is between 0 and 1. It is a product of its own inputs and its own sigmoid. It has no relationship with this one. But what do we actually want? We want to predict a word. So we want them. So essentially, we want to do an argmax here. In fact, just a max here. In सब में से max कौन सा? और argmax इस sense में कि कौन से वाले neuron के लिए मेरी highest value आ रही? That's the argmax. Okay. So what do? We do a multi-input sigmoid, aka softmax. How many of you remember your good old softmax? Easy I over some e e raised to power zi hai, by the way. Easy I, where this I goes over 1 to k. So सारे के सारे और ऊपर टॉप पर वो वाला एक्सपोनेंट में रख दिया है जिसका आप पर्टिकुलर निकाल रहे हैं. Usually we show it like this. So this is your softmax layer. So the softmax layer और कुछ नहीं कर रही, इन सब के सबको एक probability distribution में convert कर रही. So now they're summing up to be a 1. So they have been scaled proportionally in an order preserving manner. ये बातें हम याद रखनी है. इसमें कुछ ऐसा नहीं हुआ कि बड़े से छोटा हो गया या छोटा बड़ा हो गया. जो छोटे थे वो अभी भी छोटे हैं, जो बड़े थे अभी भी बड़े. relative relationship change नहीं हुए, सिर्फ सम इनका स्केल होगा, unless there is an overflow or an underflow, unless there is something like that. वो काम खराब कर सकता है, clippings हो सकती हैं. वो नहीं हुआ, सब कुछ ठीक हुआ है अगर, तो उसके बाद इसने सिर्फ इसको स्केल कर दिया between 0 and 1. So the sum of this is now 1. जी. Yeah, Z. मैं sigmoid ले रहा हूँ क्योंकि हमने न्यूरॉन के अंदर कोई छेड़छाड़ नहीं की है. But what you said is a valid thing to do. It has repercussions. All actions have repercussions. So sometimes these numbers could be so big that when you raise them to the power of e, they, yeah. So this वजह से बाज दफा जो है वो उससे प्रॉब्लम आ जाते हैं. तो because what you're saying makes sense from a different perspective कि अगर ये करने ही था तो वहां पे करने की क्या जरूरत थी, दो दफा सॉफ्ट मैक्स करने की क्या जरूरत थी. And the reason is normalization. So we'll be doing a lot of that in the future. Okay, so as a result I get a vector. मैं इसको वेक्टर बना रहा हूँ. वैसे ये आउटपुट्स हैं सारी अलग अलग. सॉफ्ट मैक्स होने के बाद उतनी ही आउटपुट्स निकल रही हैं जितनी अंदर जा रही थी. उसने उसको डिमेंशनैलिटी को चेंज नहीं किया. This vector is a really important vector. This is my y hat. What does it have? It has numbers between 0 and 1 on every location. All of these numbers sum up to a 1. कुछ बड़े हैं, कुछ थोड़े छोटे हैं. Right? Okay. The maximum one of them could be our predicted word. We can say this is the word I'm predicting, right? Or there could be other ways of predicting. इसको भी अभी देख लेते हैं. We can sample from this distribution to predict the next word. Okay. So ये आज का टॉपिक था नहीं. इसे कहते हैं आमद की क्लास. तो अब यहाँ पे आमद है, अब आमद के साथ जो कुछ भी हो रहा है वो हमने करना. Okay. So one way of predicting the next word is just to take the max from it. जो maximum number है आपका है वो predict कर देता हूँ. So यहाँ पे मैंने I भेजा था, यहाँ उसने M को highest number दे दिया. मैंने कहा I के बाद मैं M predict कर रहा हूँ. That's one way of doing that. That's a very, from the perspective of the language that will be produced, it's a very non-creative way of sampling. Because every time वो I के बाद M ही कहेगा. So the sentences will always remain dry as dirt. कोई creativity नहीं होगी. But you also, in the course of machine learning, learned another way of generating words using a distribution like this. वो तो अब आपने कहीं और से, वो आप अपने उस दूसरे कोर्स से ला रहे हैं. नहीं, एमएल में था, एमएल वो भी था. अच्छा, नहीं नहीं, एक और चीज भी थी एमएल में. Shannon visualization. How many of you remember the Shannon visualization? So the Shannon visualization was simply, you have a bucket here in which there are numbers. So there is a 0.01 and maybe like 0.09 and then the other numbers. You create this distribution between 0 and 1 और हर वर्ड की बकेट को उतना बड़ा कर दें जितना उसका नंबर है. So you have some big buckets, you have some small buckets. Now generate a random number and let's see where it falls. It will fall in a bigger bucket with more probability and in a smaller bucket with lower probability. This time, when it's going to generate, it will be very creative. In fact, so creative that it's almost going to be bonkers. तो कुछ ही बोले जाएगा, वो इतना अच्छा नहीं बोलेगा. A Shannon visualization to the numbers here, that's the algorithm. So वो ये neural net में मैं directly नहीं दिखा रहा हूँगा. We're just saying here is an algorithm, you map them and then you generate a random number and you, so you can create a, अगर show करना है neural network में, you can just say Shannon sampling and you can do it like that. Okay. Now let's see what else could we have done जो इन्होंने कहा था. So ये तो हमने कहा था उन सब के सब में से सैंपल करके लाने के लिए. That was also, by the way, this channel sampling. In this case, it's also the same thing that we call the unigram sampling. Remember पिछली क्लास में जब हम बात कर रहे थे नॉन नेबर लाने के लिए, हमने कहा था unigram sampling. सैंपल इस तरह से करो कि हर चीज अपनी प्रोबेबिलिटी के हिसाब से आए वापस. वो भी यही सेम तरीका था. We were doing the same thing. Okay. We could have said, no, not everyone gets to be a part of this game. Choose just the top k biggest values from this vector and only allow them to participate in this game. So you say, okay, I sort them all. I choose the top k. My k is equal to 1000. My k is equal to 100. My k is equal to 3. My k is equal to 7. And now generate a random number. And again, those 7 are based on their buckets are of the sizes of their probabilities. So now I get a more stable outcome. This is essentially, इसके बहुत से नाम हैं, हम आगे जाकर जब इसको करेंगे तो बहुत से नामों से करेंगे, but this is what you call a beam search. So you define a beam और आप उस beam के अंदर से कुछ ला रहे हैं. This is also known as, in another sort of a nomenclature, it's known as top K sampling. So top K, bottom K भी term use होती है. अगर you come from the HMM literature तो हम इसी तरह की चीज को beam search भी कहते हैं, वो यहाँ पर उसको भी हम use कर सकते हैं. उसी का जो एक केस है जिसमें आप मैक्स उठा रहे हैं, ये वो वाला केस है जिसमें आप बीम विड्थ को 1 कर रहे हैं. दैट्स एसेंशियली व्हाट इट मींस. ओके, ऑलराइट, रिगार्डलेस, यहां तक तो पहुंच गए. एक वर्ड अब प्रिडिक्ट हो गया आपके पास. एट दिस पॉइंट आई वांट टू क्रिएट अ लॉस एंड प्रोपेगेट इट बैक. सो हाउ डू आई क्रिएट द लॉस? I take the y, the actual word in the corpus. Remember, this is self-supervised. There is a word there. I के बाद कुछ तो था जब हम ये predict करने निकले थे. So this thing, this is a one hot vector. This has all zeros, and there is just a one somewhere here. My loss function, if I'm using the cross entropy loss, if you remember what the cross entropy loss would look like, let me just show you that. आप सब कुछ इतना कुछ आज निकलवा चुका हूँ कि मैं और नहीं चाह रहा. So I just want to bring this up for you. Okay. This is what it's going to look like. So this y is going to act as a gate. It's going to choose the y hat जो कि होना चाहिए था सही में. And then based on this, it's just trying to find out ये इससे कितना दूर है. So it's saying तुम्हें कहना चाहिए था m. तुमने m predict किया with a probability 0.03. Your distance from the true answer is 1 minus 0.03. This is how much you go back and you tell all of them to change themselves so that next time when you produce an answer in this position, they should have a number which is bigger than 0.03. That's the semantics of the gradient descent that's going to happen here, of the back propagation that's going to happen here. सबको ये बात समझ में आ रही है? सब लोग मेरे साथ हो? ठीक है? जी 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 sure. Here? No. This is a one hot vector. It will have just one because in the corpus you do this usually word prediction task के लिए you fit to a corpus to a data set में लिखा हुआ I am a person who has been living in Lahore something like that so उस आय के बाद एक actual word आया हुआ है किसी और आय के बाद जब आगे जाएंगे तो हो सकता है आय के बाद कोई और word आया हुआ I was आया हुआ I will आया हुआ नहीं no collections. This is not yeah, the way we were training last time. This is not contrastive loss. You are actually going over just your entire corpus, taking in a word. So first word of the corpus to predict the second word of the corpus. Now second word of the corpus to predict the third word of the corpus. Each time you're propagating the losses back. Yeah. एक एक करके कर रहे हैं वी डूइंग स्टोकेस्टिक ग्रेडियंट डिसेंट एक मर्तबा भी जब आप पूरी कॉर्पस से गुजर चुके होंगे तो ये वेट्स बड़े जान में आ चुके होंगे and then maybe after like one or two more of these epochs you're almost done. So this is the total loss because ये sub zero है and if you focus there that formula is saying j is equal to 1 to c in this case is the length of this one out vector so that's going to be j is equal to 1 to v and here yj into log y hat j only one yj in this entire vector is 1 everything else is 0 so the entire loss will be based on just this y hat so your cross entropy loss for one hot vectors becomes like a switch कि वो राइट आंसर से सिर्फ उसकी वैल्यू को कंपेयर करता है कि जो वर्ड प्रिडिक्ट होना चाहिए था उसको इसने कितनी प्रोबेबिलिटी दी है एंड दैट्स इट if the probability चले if the probability is high if the probability of y hat is high then the loss of the probability is going to be low if the probability is low then the loss is going to be high अगर करते जी 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 या नहीं so if you're doing let's say top k उस top k के आखिर में भी you're gonna just give me an output for a single new एक word जिसे आप choose कर रहे होंगे उसमें से so let's say you're gonna roll a die across the top seven you're gonna choose one अब सिर्फ ये वो है जिस so इसके इसके थ्रू आप word predict करेंगे right but now you give up word predict आपने कर दिया है ये लॉस फंक्शन कैलकुलेशन पे उसका कोई इंपैक्ट नहीं इट डजंट नो सो जो वर्ड सो बेसिकली एसेंशियली यू थिंक ऑफ इट लाइक दिस ये मैच है वो प्रैक्टिस थी वो आपका इंटरनल काम है उस प्रिडिक्शन से होना आइडियली ये चाहिए था कि ज्यादा चांसेस हो कि इसके कॉरेस्पॉन्डिंग वर्ड जो है वो वाला चूज हो रहा हो जिसकी हाई प्रोबेबिलिटी हो या वो इस पे इंपैक्ट नहीं करता गुड क्वेश्चन या and what do you mean by sari values yeah but how would you have more values of y hat here more than one word hmm 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 agreed I agree that the process is slow. But my question to you is there even a way which would make sense to make it faster? Like we are giving in one word and we want to predict what's the next word. एक word के आगे एक ही word आ सकता है लिहाजा एक ही y जो है वो यहाँ one हो सकता है I cannot say कि इस word के आगे multiple words आ रहे होंगे I can just given one word I can do one word so even if I would have given multiple words still I would have predicted just one word तो yes it is slow कि एक एक word एक वक्त में predict हो रहा है but this slow process is kind of what we are stuck with if you're following this training formula that you just predict one next word And if you want to predict more than one next words, then you need to fix at least one next word in order to predict the word after that. So that we get into back into like the chicken and egg problem. कि एक predict करेंगे तो उसकी base पे अगला करेंगे. ठीक है? Is that clear? जी. Yes. हाँ उसके लिए सो हम इसमें बैच तो ना कर सकते उसका तो मतलब होता है पूरी कॉर्पस के ऊपर एक दफा बैक प्रोपेगेट करो हम वो ऑब्सो करने को कर सकते हैं लेकिन उसकी कोई यदि बहुत ही स्लो होगा फॉर लाइक अ मिलियंस ऑफ वर्ड बिग कॉर्पस so what you do is you can do a mini batch so for a few words keep accumulating the losses and then propagate them लेकिन that's usually not done you do it after every word. Yeah. So that's what you're suggesting. That's a good point. What you're suggesting is essentially just an optimization. कि वो कैसे कर सकते हैं. We'll get into a lot of that. So after we are done with the transformer, we're gonna get into lots of optimizations. Yeah. C ये जो capital C, yeah, capital C is the length of this vector V. No, so वो टॉप के सिर्फ एक साइड थॉट था जो मैंने आपको दिया था वो यहाँ पे अभी हम डिस्कस नहीं कर रहे वी जस्ट डिस्कसिंग द सॉफ्ट मैक्स हियर बट इफ वी वुड हैव डन दैट दैट टॉप के वुड नॉट हैव फिगर्ड बियॉन्ड दिस टॉप के का सिर्फ काम ये था कि वो कौन सी वाली चीज को एज अ प्रिडिक्शन चूज करता है कौन सी वाली चीज को विन करवाता है लेकिन जिससे वो कंपेयर होना था वो तो एक्चुअल वर्ड था जो कि कॉर्पस में मौजूद था सो यू आर नॉट हिटिंग दैट एट ऑल so the top k was not changing the probabilities in any way. Yeah. No, because the Y doesn't know that. So think of your Y as an actual. So think of a Wikipedia page that has text on it, and you start giving one word at a time from that Wikipedia page, first word, second word, third word, to your neural network to predict the word after that, and you have an actual word after that. So this Y is one for that actual word in the Wikipedia article, and you're just testing your neural network whether it's able to correctly predict that next word or not. That's what you're doing. Okay. All right. Ready for some interesting news? What you've just done is to train word to vec using approach one. When this training is done, this layer has trained embeddings for the entire vocabulary. Remember जब मैंने पहली दफा आप लोगों को ये इंट्रोड्यूस कराया था बहुत से लोग पूछ रहे थे कि why does every slide say this is too expensive and remember now notice that you are asking me questions and मेरे ख्याल में कोई 5 क्वेश्चन इसी लाइन पर थे कि why this is so expensive so now the purpose has been served ये हो गया दिस वॉज वर्ड टू वेक वर्ड टू वेक की ओरिजिनल आइडियोलॉजी जो पेपर आपने पढ़ा था वो आइडियोलॉजी सिर्फ ये थी कि आप एक कॉर्पस पकड़े नेक्स्ट वर्ड प्रिडिक्शन का टास्क लें उस टास्क से पूरी की पूरी कॉर्पस पे ट्रेन कर लें जब ट्रेन कर लेंगे तो ये जो दरमियान की लेयर होगी इसमें एक बाय प्रोडक्ट पड़ा होगा जो खुद ब खुद बन रहा था द वेट्स विच वर एसोसिएटेड हियर द वेक्टर का साइज जो था वो एल था सो लेट्स से 300 डिमेंशनल वेक्टर जो यहाँ पे बन रहे थे हर वर्ड के लिए एक वेक्टर बन रहा था remember so okay let's convince ourselves super convince ourselves here if even that's a word uh, if I said a one here that one let's say यहाँ word है an word का one कहाँ कहाँ जा रहा है यहाँ उन सारे के सारे 10,000 वेट्स में से वी वेट्स में से एक वी इनपुट्स में से एक एन का वन है ये एक यहाँ एक यहाँ एक यहाँ एक यहाँ सब में एक एक वन जा रहा है वो एक एक वन एक एक डब्ल्यू को सिलेक्ट करवा रहा है एक एक रो को एसेंशियली सिलेक्ट करवा रहा है वहां से so when you basically do this when you have a one in the one hot vector so okay let me do that l into v into v into one okay so let's say 300 into 10,000 into 10,000 into 1 gives you 300 into 1 what is this 300 that is the embedding of that particular word ये हमने पिछली क्लास में भी हमने बात की थी जब हमने वो पीडीसी के वो ट्रेस की बात की थी remember that's the same thing happening okay so this is where you're training the embeddings now I want to take you यहाँ तक थोड़ी आना था यहाँ से आगे बढ़ना था now I want to take you a step further okay now you're ready to understand the difference between skipgram and SIBO SIBO says use multiple words which are actual neighbors to predict one word. So this thing has बहुत तवज्जो से इसे देख के अब इसकी कैलकुलेशन अपने दिमाग में शुरू कर दें कि इसकी dimensions क्या होंगी. So this is word W, let's say T minus 2, WT minus 1, WT plus 1, WT plus 2. And this thing, what you get out is WT. SIBO uses the context words to predict the target word, right? Okay. And SIBGRAM uses WT to predict WT minus 2, WT minus 1, WT plus 1, and WT plus 2. That's the difference between SIBGRAM and SIBO. होता रहे हमारा मसला कुछ और है. For this vector, okay, now this is an important question. It is supposed to have two answers, one of which is nearly right, the other is right. इस न्यूरल नेटवर्क में इनपुट लेयर का साइज क्या है? रेज हैंड्स. डायग्राम देखकर एक जवाब जहन में आएगा. वो जवाब सही है. थोड़ा सा सोच के एक और जवाब जहन में आएगा. वो जवाब ऑप्टिमल लगता है. वो जवाब हमें इतना अच्छा लगेगा कि उसकी कोई बुराई नहीं नजर आएगी. Until we're able to find that. So I want to reach there. Who can tell me the dimensions of the input layer? चार वर्ड है. चार वर्ड इनपुट में जा रहे हैं, वन वर्ड आउटपुट में आ रहा है. आप लोग माहिर हैं इस तरह की चीजों के, ये लिए कोई मसले वाली चीज तो नहीं. दी इनपुट इसका साइज कितना है? पूरी लेयर. चार कॉन्टेक्स्ट वर्ड है. यहां गलती की है. एम्बेडिंग से क्या ताल्लुक है? एम्बेडिंग तो भी आई नहीं. वर्ड टू वेक्टर तो भी ट्रेन होना है. इनपुट लेयर है, इनपुट लेयर. वो हाँ, वो क्या है? So vocabulary size. So this is V. This is also V, one hot. This is also V, and this is also V. So this is 4 into V. This is even more wasteful than the last time. We have not gotten better, we have gotten worse. हम बिगड़ते चले जा रहे हैं. पहली क्लास है अभी हमारी जब हमने न्यूरल नेटवर्क्स बनाना शुरू किए हैं, और हम कितने 1 घंटे 10 मिनट में इतना बिगड़ गए हैं कि हम कह रहे हैं जितने वर्ड्स है उतना कर दो. Why not? Okay, is the question. Why not just have one hot vector of size V and put ones in places of all words जितने वहां पर थे? Now find the answer for me. The words were, for example, the quick brown fox jumps. So my target word is WT. This is WT minus 2, WT minus 1, WT plus 1, and WT plus 2. What I'm saying is it's perfectly fine to have a one hot vector for this, for this, for this, for this. That means we have an input layer of size 40,000 if my vocabulary size is 10,000. So I'm talking about 4V. Why being so wasteful? Why not reuse the same neural network जो अभी चंद मिनट पहले आपने बनाया है, and just have ones in the places of the quick, fox, and jumps? Would there be any problem or not? Would there be any new problem or not? कुछ तो इसमें भी होंगी ना. एक मसला कोई ना कोई जरूर कहेगा. ओके, I'm just planning to bet against myself कि कितना मैं अपने आप को पैसे दूंगा अगर उसने किसी ने ये कहा. ओके, I have a bet in my head. नहीं, आप नहीं सर. पहली दफा मैं पकड़ लिया. I lost against myself, so no problem. मैंने अपने आप को ही खिलाना था जो भी खिलाना था. ओके. सो आई लूज आई विन. ओके, सो एब्सोल्युटली राइट. पहली नजर में आम तौर पर जो एक एतराज आता है इस अप्रोच के ऊपर ऑफ यूजिंग ए सिंगल वन हॉट वेक्टर इज के वर्ड ऑर्डर नहीं रहेगा. until we realize कि word order तो वैसे ही नहीं रह रहा. A neural network has no priorities of its inputs over the other. There is no context, there is no sequence. That's your feed forward neural network. That's what you've been living with for the entire last semester. So लिहाजा ऑर्डर तो है ही नहीं. हाँ, मसला तब आएगा अगर मैं कहता यहां पर कोई दो वर्ड रिपीट हो रहे होते, द क्विक ब्राउन क्विक जंप्स. सो अब ये दो क्विक्स को मैं कैसे इंडिकेट करता. सो पहले काम करने के लिए तो मैं ये एतराज कर सकता था कि जी आप वन हॉट वेक्टर को वायलेट कर रहे हैं. हमारी पूरी फील्ड ही इस काम पे खड़ी हुई, हम चीजों को वायलेट करते हैं. हम रूल्स वायलेट करके पूरी मशीन लर्निंग बनाते हैं, तो वी डोंट केयर एक वन हॉट वेक्टर से क्या हो जाता. बट द प्रॉब्लम इज के यू कैन नॉट रिप्रेजेंट रिपीटेड वर्ड्स, वेयर एज फॉर दिस यू कैन रिप्रेजेंट रिपीटेड वर्ड्स. इसकी बुराई करो. आई एम बर्निंग टू हियर समथिंग रियली बैड अबाउट इट. बस तमीजदाराना अल्फाज में कर दी. इसकी बुराई करो. इसमें एक बहुत बड़ी बुराई मुझे नजर आ रही है, मुझे इससे नफरत हो रही है. वो बुराई क्या है इस मॉडल की? जितनी बड़ी कॉन्टेक्स्ट विंडो है उतनी टाइम्स वी के मुझे इनपुट वेक्टर लगाने पड़ रहे हैं. और जिस दिन ये न्यूरल नेटवर्क बना है उस दिन ये पता होना जरूरी है कि कॉन्टेक्स्ट में कितने वर्ड्स होंगे. सो इफ आई एम डूइंग अ वर्ड प्रिडिक्शन टास्क, इफ आई एम सेइंग फोर वर्ड्स की बेस पे फिफ्थ वर्ड प्रिडिक्ट करो, तो ये न्यूरल नेटवर्क फोर वर्ड से फिफ्थ को प्रिडिक्ट कर सकता है. जस्ट ट्रेन इट डिफरेंटली. बट ये सेम न्यूरल नेटवर्क फाइव वर्ड्स देकर सिक्स को प्रिडिक्ट नहीं कर सकता. उसके लिए नया न्यूरल नेटवर्क बनाना पड़ेगा. द फिक्स साइज इज अ बिग लिमिटेशन. अच्छा चले, अभी हम इसके साइज बना रहे थे. सो दिस वाज 4 into v. We're all convinced, right? We're all right with that. Okay, how about this layer? Tell me the size of this layer. This is your SIBO, classic SIBO. पेपर भी पढ़ के आए हो तुम लोग इसके ऊपर. I was feeling better until I realized that. You even wrote a review of that paper. I'm feeling worse and worse. Okay, barely able to stand. Okay, so yeah, इस लेयर का साइज बताओ मुझे. V times the embedding size. Okay, एम्बेडिंग साइज तो मुझे समझ में आ गया कि यहाँ पे जो न्यूरॉन्स हैं वो इंडिपेंडेंट हैं इस चीज से कि ये चार वर्ड थे या छह वर्ड थे या 100 वर्ड थे. ये न्यूरॉन्स तो उतनी ही रहेंगे. मीनिंग मेरा एम्बेडिंग साइज मेरी मर्जी है. मैं 300 ही रखना चाहूँ 300 ही रखूँ, 50 रखना चाहूँ 100 रखना चाहूँ, वट एवर. बट द पॉइंट इज हाउ मेनी इनपुट्स आर नाउ फ्लोइंग इन टू दीज न्यूरॉन्स. 4V, 40,000. Each neuron, instead of getting 10,000 inputs, is now getting 40,000 inputs. So the vector, and stay with me, stay awake, stay with me. These things are gonna come back to you. This is a big one. Four words, eh? So the matrix of this embedding layer is now going to become 40,000 into 300 matrix. 40,000 inputs आ रही हैं. इससे 10,000 आ रही हैं, फिर इससे 10,000 आ रही हैं. हर इनपुट का एक एक वेट है. So it has 300 neurons. Each neuron has 40,000 weights. जी. या वो पेपर को भी छोड़ दें. सो पेपर के अंदर वो उसको कर रहे थे, क्या कहते हैं उसको, पूलिंग कर रहे थे. दे वर डूइंग मैक्स पूलिंग, फॉरगेट मैक्स पूलिंग. वी आर नॉट डूइंग मैक्स पूलिंग. सो वी जस्ट यूजिंग अ कन्वेंशनल न्यूरल नेटवर्क हियर. So in the conventional neural network, this is going to be 40,000. So we're going to get to poolings eventually. Okay. And then यहाँ पर जब ये 300 क्रॉस 1 में आ गई चीज, तो now we can just go ahead और यहाँ से आगे के sizes बिल्कुल वही रहेंगे जो पहले थे. As your personal homework, I'm not going to check that. I'm not going to do anything with that. Based on the same model, you should find out all of the dimensions of this matrix, of this neural network. Especially in the end, when you're going to do your softmax, what would the softmax be against? Would there be one softmax or would there be four softmaxes? Is the question. Right? So मैं जवाब नहीं दे रहा, आपने खुद जाके सोचना है इसके ऊपर. The answer should be super obvious to anyone who was paying attention throughout और साथ साथ था. The answer should be like super obvious or duh, it's like that answer. But like if you're not getting that, then think about that. Okay, stay with me for just 2 more minutes. I have one last detail to add जिसकी बेस पे मैंने अगली क्लास पढ़ानी है. So this is your feed forward neural network processing language. इनको हम neural language models भी कहते हैं. This was your first example of a neural network predicting a word. A discriminative model not designed for generation, generating. It was a big deal for us when this initially happened. The problem with this is that this does not have any concept of word ordering in its inputs, even if we add the words, and it does not allow for flexible sized inputs. दो इनपुट की बेस पे वर्ड प्रिडिक्ट करना है तो और साइज का न्यूरल नेटवर्क होगा, चार पे करना है तो और होगा, 50 पे करना है तो और होगा, और आजकल के मिसाल के तौर पे जेमिनाई का कॉन्टेक्स्ट साइज जो है वो 1 मिलियन टोकन है. Are you seriously telling me there are 1 million inputs in there? Kind of, yeah, because we have come back to feed forward neural networks again. So there is a 1 million size there, but we're gonna get there eventually. और उससे पहले हम कुछ और करके जाएंगे. So now I'm just giving you one idea. जो चीज मैं बयान करने लगा हूँ, I did not find it in any book. So मैंने काफी ज्यादा ढूंढा था जब मैं पहली दफा स्लाइड्स बना रहा था. People just assume that this is such a simple detail that they never mention it. Therefore, I'm mentioning it. If I were to convert this entity into a neural network which has state built into it, what do I mean? Remember your combinational circuits? How many of you watched my lectures on in 2 to 5? Quite a few. Okay. So, for those of you who did watch, there were two types of circuits. There were combinational circuits, your multiplexers, your decoders, your encoders, and so on. And then there were sequential circuits. Sequential circuits were state machines. So the output of a combinational circuit just depended on the inputs of the combinational circuit. जो input देंगे वही output में आ जाएगा after the propagation delay. Remember? That's like your feed forward neural network. Now, if you add the concept of state into a neural network, what would that mean? Remember the sequential circuit जिसमें आपने एक loop लगा दिया था, जिसको मैंने पहली दफा ये कहा था कि तार में अगर बिजली पकड़ लें और फिर ये कहा था कि किसी फिजिक्स वाले बंदे ने सुन लिया तो बहुत नाराज होगा. So if we add in a loop, hence a flip-flop, you say that now this neural network produces an output which is dependent on two things: the current input and the previously stored state of the circuit. This is what we are about to convert our neural network into. The way we write that in an abstract manner, again, stay with me for a few seconds. इस मौके पे अगर मैंने आपको lose कर दिया तो मुझे अगली दफा बहुत मेहनत दोबारा करनी पड़ेगी. This is your feed forward neural network. This takes in a word or words, outputs a word or words. If I want to say, no, no, I want to give you a word, you process it. Now I want to give you another word. And you process the second word in the context of the first word. So you should remember what you processed first. So it says, okay, that means I need a memory. So I need to retain my hidden state and pass it back to myself as an input the next time when I'm processing the next word. So when I'm processing word t plus 1, I'm reusing this input from the time when word t was processed. So I give it word t, it produces ht, and then I give it word t plus 1, and it gives ht back to itself from the last time. It has stored it somewhere, and it uses that this time, and there is a weight which gets multiplied with this input that comes back. Now today, this is what we're going to unfold next time. Quite literally, we're going to unfold it next time. But the only thing that I want to mention today, जिसके बारे में मैं कह रहा था कि किताबों के अंदर मुझे इस तरह से बनी हुई नहीं अक्सर मिली, what is it that you retain in this entire thing? वो है क्या जो कि आपकी स्टेट रिटेन करता है, जो बन रहा है, बाय द वे इसको हम रिकरेंट न्यूरल नेटवर्क कहते हैं, RNN, and what it retains are these things after multiplying them with a weight. So इसके पास है क्या? 10,000 inputs. It's going to pass those 10,000 things back to itself after multiplying each one of them with a weight. So there's going to be another matrix of the size of the weights that it was holding. It multiplies each weight with that, processes it back, and now it's getting an input from here. So my previous state and what I'm getting now, this is going to produce the next word. So this was a big revolution. This is also a big phase in the course. We're gonna enter another philosophy of these neural networks. We're gonna spend some time here. We're gonna do detailed back propagation, forward propagation on these. We're gonna get then again like everything इनकी बुराइयां करेंगे और फिर इससे अगले एक मॉडल पे जाएंगे और फिर जो मॉडल आएगा उससे अगला that's the one that we really love these days. ठीक है, थैंक यू सो मच. अगली क्लास में आपका क्विज है, पढ़कर आइएगा. और ये जो कुछ मैंने किया है इसकी कोई स्लाइड्स नहीं है, तो जो आपने बनाया है वो आपने बनाया है, बस आप सब लेकर जा रहे हैं. किसी स्लाइडों की उम्मीद ना रखिएगा, मैंने यहीं पे ही बनाया. दिस वाज ऑल, मोस्ट ऑफ इट दिस वाज आमद. तो या